Okay guys, so we're going to start chapter 14, water resources. This will be our first lecture, and our primary focus here is looking at water as a resource and some of the problems there. We're not going to touch too much on water pollution. We have a whole another chapter 22 associated with that. We're just going to kind of look at how we use water, how we manage water, some water problems and management, etc. All right. This particular lecture, though, will be over the first two sections of the textbook, so page 308 through 317, the importance of water and water use and resource problems. There's a lot of vocab, so in class, you guys should get a study guide from me. I want you guys to use that study guide and your text to kind of keep track of the vocab on your own. As you are the bright AP students that you are, you ought to be able to manage that kind of stuff on your own. So I'm going to throw some vocab at you while I'm talking. And if you're not quite catching on what that is, just use your textbook and try to follow along as best you can. All right? So first of all, we're looking at water itself. We do need to understand a little bit about the chemical properties of water. All right? As you all know, water is 2 hydrogen and 1 oxygen, right? So we write that as H2O, okay? It exists in 3 forms right here on Earth. One of the nice things about our planet is it is in that range where we get water as both a solid, as a solid, liquid, and as gas. All right, that's important for our hydrologic cycle and for life. Has a relatively high heat capacity, so we talked about that specific heat of water being higher. So it both heats up and cools off more slowly than surrounding land. And it's polar. Okay. Now, what we mean when we say that water is a polar molecule is that because there's a kind of a large difference in electronegativity between hydrogen and oxygen. And by that, I mean, certain atoms attract electrons more strongly than do others, right? And if there's a big enough difference between that attraction, that means that when hydrogen and oxygen bond, the oxygen attracts electrons a little more strongly than the hydrogen does. So when that happens, we get a little bit more of a negative charge on the oxygen, a little bit more of a positive charge on the hydrogen. And we call that a polar molecule. All right. Now, because of water's polarity, it forms these little hydrogen bonds with other molecules of water. So that's part of the reason why water kind of sticks to itself, right? So you maybe did that experiment like in elementary school where you can put little drops of water on top of a penny and try to see how many you can get. So water has this tendency to stick to itself. That's because the partial positive and partial negative of that side attract, okay? Now, the flip side of water's properties and being polar is that because of its polarity, it's really, really good at dissolving things, okay? Which also makes it really, really easy to pollute, okay? So, water is never completely pure in nature. So as soon as water is exposed to air, for example, it's going to start dissolving oxygen and start dissolving things like carbon dioxide. So it's always going to have a few dissolved gases in it. As soon as we expose it to solids, right, there's always trace minerals, and water can dissolve a lot of minerals. All right, and that's why oceans are salty. Now we'll get into how bodies of water become increasingly salty over time at another time, a later date, but because water can dissolve minerals, certain bodies of water under the right conditions become salty over time, like the oceans and our inland seas and the Great Salt Lake, etc. All right. So salty water is a normal natural phenomenon, but water, again, because it's so good at dissolving things, it's very easy to pollute with other unnatural substances. All right. So if we look at water globally, right? We are a water planet. There's water all over the place. So you might be wondering, why do we talk about things like drought and water shortages? Well, part of that reason is of all the global water, only 2.5% of it is actually fresh water, the type of water that we can use for drinking and cooking and cleaning and irrigation and industrial processes. We need fresh water for that. So only 2.5% of our global water is fresh water, and 2% of that 2.5%, so 2% of the global water is in the form of ice. So it's locked up in Antarctica and Greenland, essentially. That's leaving a measly 0.5% of the water available on Earth as available fresh water, either from aquifers or reservoirs or surface water. Okay? So, yes, we have a lot of water on Earth, but only 0.5% at any given time is actually available for us to use for what we need it for. All right? So there's some freshwater terminology. Again, use that study guide in your text. It's going to be really important you follow up on your vocab. But for the water that we tend to use, the fresh water, okay, it's usually either locked up in a stream of some sort. So creeks and rivers, it's locked up in a lake or a reservoir sometimes, which would be essentially a man-made lake behind a dam. Or it's locked up in our underground reservoirs that we call aquifers. And so some of you guys, if you have wells on your property, that's what you tap it into. You just dig a hole through the ground till you get to the aquifer, and you pump the water from that aquifer up to the surface, and there's your well water. Okay? As far as types of aquifers go, we have confined and unconfined. Okay, so an unconfined aquifer gets direct recharge. So water hits the surface, some of that water becomes runoff, goes to the stream, some of that water percolates through and directly feeds our unconfined aquifer. All right, we call that infiltration or percolation. Okay, so runoff being the water that stays at the surface, feeding our rivers and streams. Infiltrated water is water that percolates through the soil and feeds our unconfined aquifer. Now, a confined aquifer generally tend to be deeper, and essentially what a confined aquifer is, there's a layer, impermeable layer. All right, typically that's going to be clay, by the way. Sometimes could be something like shale, but typically we have a layer of clay. And clay is not good at letting water percolate through. One of its properties is a very, very low permeability. So because of that, we have this layer of water on top of it, which is our unconfined aquifer. But sometimes beneath a layer of clay, we have a separate aquifer, a deep water aquifer, that is not getting directly recharged. Now, our deep water unconfined aquifers tend to be a little larger. And they're kind of a really large supply of groundwater, but they're also much, much slower to recharge. So yes, they do recharge, but they tend to recharge from farther away, and it just takes more time for the water to work its way to that confined aquifer. Okay, so sometimes we call the wells that we drill into our confined aquifer artesian wells. Okay, and some of those artesian wells, those confined aquifers actually have a fair amount of pressure. They don't need a pump. The water just comes right out. Okay? So that's just some terminology. It's important we understand that a lot of the water that we use, a lot of it is locked up underground for us. Alright, so water use and resource problems falls into three categories. First of all, we've got too much water, alright, which we would recognize as flooding, too little water, which we often refer to as drought. And then, of course, there are the cases where we have poor water quality, which we're talking about polluted water or diseased water, which again, discussed more in a later chapter. That's 22, by the way. All right, so when we have too much water, yes, we refer to that as flooding. Now, flooding is a natural phenomenon. Places are going to flood. It's just a common experience, really typical in springtime. Sometimes in the summer, if you get some really heavy rains, flash floods are more common in the summer. Our more chronic floods happen more in the spring with some melt and stuff like that. Okay? So when we say human-induced flooding, though, we're not talking about humans affecting the amount of precipitation. We're talking about how humans alter systems so that flooding becomes maybe worse or exacerbated due to changes in the system. All right? So modern floods are highly destructive, partly because we remove water-absorbing plant cover from the soil. Okay, and then we construct buildings and roads and stuff like that. And that's going to affect how much water the ground is able to absorb and how much becomes runoff. We'll talk about that a little bit too. And then certain ecosystems like wetlands are really good at mitigating floods. They absorb those floodwaters, slow them down, and prevent it from reaching other areas. We're in a bad habit in the mid-20th century of removing wetlands. We kind of thought them as wastelands for a long time. All right, so floodplain, that's one of your vocab terms, but I did want to take one moment to actually describe that term because I'm going to refer to floodplains quite a bit. But a floodplain is an area bordering a river channel that has the potential to flood. And yes, you and I live right smack dab in the midst of a floodplain right here in Walla Walla. All right, so again, human-induced flooding. We're not causing the precipitation that causes the flooding in the first place. We're changing the system so that the system is less able to absorb heavier rainfall or perpetual rainfall like we see in the springtime. Okay, so in the case of a pre-urban floodplain, you have to remember that if plants and animals are living in a floodplain, that probably means that they have a specific set of adaptations that allows them to coexist with the occasional flooding that occurs. All right, so we look at the precipitation falling in a pre-urban floodplain, so undeveloped. Okay, 40% of that water by plants gets put right back to the atmosphere again. Okay, 50% of that percolates through the soil, and only about 10% of that precipitation actually becomes runoff. Now, in the event of really, really heavy precipitation, that percentage might increase a little bit in the short term. But we're talking a relatively small percentage of that water actually becomes runoff that contributes to flooding. All right, now if we contrast that with an urban floodplain, so we put sidewalks and streets and houses and parking lots on the surface. Those surfaces do not let water percolate through very well. And so as a result, even with some yards and so on, we change drastically the amount of water that becomes surface runoff. And it's the surface runoff that contributes to flooding. All right. So we cut the amount of evapotranspiration because we're removing plants that do that for us. Right. We cover our surfaces with lots of impermeable surfaces. So we greatly reduce the amount of water that's able to percolate through the soil, resulting in a pretty significant increase in surface runoff, up to about 43% in our urban areas, as opposed to just 10%, right? So in a heavy rainfall, the vegetation and soil and evaporation might be able to handle that and maybe have a small flood. In an urban area, that flood can become much more problematic because of the increased surface runoff. All right, so a floodplain. Why do people live on floodplains in the first place? Good question. It has to do, first of all, easy access to water. So floodplains are near rivers. People tend to settle near rivers because it's easy access to water. The soil in floodplains tends to be very nice. The particle size carried by rivers, we call that silt. Silt is a great particle size for soil. It's got good properties of being able to hold water but not get waterlogged. Allows it to drain and stuff like that. And so people have built in floodplains. We tend to construct levees to help channel water away and move it and help prevent our small-scale flooding. Those levees, though, can actually fail. And so there's kind of this ongoing debate. You know, if someone decides to live in a floodplain, right, should the government help them out when it floods? Not if it floods, but when it floods, because floods are going to happen. All right? And so we build levees. The Corps of Engineers right here in Walla Walla built that concrete channel to put water through Walla Walla as fast as we can to help the flooding that will occur from time to time from damaging the surrounding areas. But we've learned some lessons. All right, because levees can fail, and when levees fail, then we run into some really nasty situations where We get some really catastrophic floods. People die, property damage, billions and billions of dollars lost to the economy. It's bad news. Okay, so one of the things we've learned is our traditional levees adjacent to a river, we channelize that river, right? And what that, again, the reason we do that is that lets water move through quickly. And part of the problem with flooding is the river system can't move the water through fast enough. All right? And so when you channelize something, you allow it to move through faster. So that's exactly what we've done right here in Walla Walla. We put that concrete channel, it's very low resistance, water can move through there really, really fast, greatly reducing the probability of flooding in downtown Walla Walla. Now, sad to say that increases the chance of flooding downstream, by the way. So people that live in, Tushy and so on, more likely to get flooded because Walla Walla is less likely to get flooded. Side note there, all right? So traditional levees are like that. Now, one of the things we've learned, particularly as a result of 1993 flooding along the Mississippi River, I will talk about that shortly, is when we construct our levees, right, rather than channeling that river, we move the levees back, all right, and we keep a certain area along that river with native vegetation. Again, what that does is that allows that river to partially flood, right? And it allows the soil surrounding the river to absorb a lot of that water, allows the vegetation to help transpire and keep soil in place. And what that does, we still have our levees, we're still protecting our surrounding farmlands, we still have places adjacent to our river, easy access to the water, right? But this helps to minimize damage caused by flooding. Because again, it's the areas right next to a river that are most prone. Really, really bad floods might surge beyond these levees, but we're talking much, much lower probability of property damage when we use this system with our levees set back and letting nature do part of the work for us as opposed to trying to channelize that river. All right, so highly recommend you guys read the case in point from pages 314, 316. It's a perfect example of what we just talked about there with levees failing and prolonged rain and so on. All right. Now, moving on to situations where we have too little water. Right. Go figure. This is in our arid and semi-arid areas. Okay. Now, because of groundwater, so in areas where the precipitation itself is not enough to provide water for agriculture. So that's our semi-arid grasslands, which do have pretty darn good soil, but the precipitation is not frequent enough, or maybe it comes in bursts and so on, so we rely heavily on groundwater, okay? So there, climate cycles, right? We've learned a little bit about that throughout this year, but there's periods of drought where rainfall in maybe 2-3 consecutive years is less than the average, right? And then sometimes that's followed up with greater than average, resulting in this average rainfall. All right. So in these areas, though, because of the good soil and because there is ample groundwater supplies, we drill wells and we pump and we irrigate from wells. All right. But in our times of drought, right, when we're not getting very much rainfall, we're drawing the water out of those aquifers significantly faster than it recharges. And so those aquifers slowly decline, getting less and less water in them. And one of the things we've learned is the groundwater is part of the structural integrity of the underlying strata. Okay? And so when we pull water out of these vast underwater reservoirs, we're reducing the structural integrity, and we actually get a process called subsidence. That's where the ground actually sinks over time. It's a slow process. We're not talking about a rapid opening of sinkholes, which do also occur. We've seen that happen in Florida actually a few times. Subsidence is just a slow sinking of the ground because we're taking essentially matter out of the ground, and the soil and rocks slowly settle to fill in those gaps that were at one point filled by water. That's subsidence. Now, in more drastic cases, we kind of open up these caverns that we didn't know about. All right, water kind of helped keep the overlying strata in place, but we empty these caverns of water, and then the overlying strata collapses into that cavern, And those are the sinkholes you hear about sometimes. If you just go to Google search sinkholes, you'll see some pop up occasionally. It's essentially a sinkhole. These holes open up and swallow houses, people, whatever. All right. Other problems with too little water, aside from loss in agriculture and so on, is along coastal areas. So let's say you live along the coast and you're relying on groundwater. Now, we have groundwater that also meets ocean water. So the salty water from the ocean isn't just along this border along the beach. It actually makes its way into the ground near the coast. All right? And so as you pump a well, there's a fresh water is less dense than salty water, so it tends to sit on top. So you can pump that fresh water out for a while. If we pump this water out too fast, though, right, that reduces the pressure down on this ocean water, and the seawater tends to make its way into the freshwater aquifer, and we call that saltwater intrusion. And as we start pumping more and more, reducing the amount of fresh water, and then all of a sudden we're pumping salt water out of our well as opposed to fresh water. And that's going to kill plants. That's undrinkable. It causes all kinds of problems. All right, this lecture is getting a little long, so I'm going to halt it here. That's the end of it anyways. Again, make sure you follow up with the reading of these sections, please.